We talked about Dalton's atomic theory and that a couple of his ideas were not quite correct. He said that all atoms of a given element have the same mass. And we just learned that different isotopes have different numbers of neutrons, and so they have different masses. The mass of an atom used to be called atomic weight. And you'll still hear that sometimes. But usually we call it atomic mass because that's more accurate. So what we do is we calculate an average mass for all the atoms, the isotopes of a given element. And of course we can't, you can't literally find them all and weigh them. So it's kind of a weighted average. We'll look at that. But that number under the element symbol. So here's chlorine, and under its symbol is 35.45. That's the mass of an average chlorine atom. There's actually no chlorine atom that weighs 35.45. But how often do you do experiments with a single atom? You don't. You do things with billions and billions of atoms, and so the average is what's useful. So that's the average mass. Average mass of all the isotopes that compose that element, and it's calculated using the natural abundance of the different isotopes. So if we look at chlorine, 75.77% of chlorine atoms are chlorine-35. Chlorine-35 atoms have a mass that's very close to 35 atomic mass units, but it's not exactly. They have a mass of 34.97 atomic mass units. The rest of the chlorine, 24.23%, is chlorine-37, and those have a mass of 36.97. And so we can calculate the atomic mass, the average. So you're more familiar with doing an average where you take all the things and you add them together and you divide by how many things there were, right? That works if you've got a few things. You know, if you've got 50 gazillion things, it doesn't work anymore. So we weight it according to its percentage. So 75.77 out of 100 are going to have this mass. So 0.7577 times the mass of that element gives us this mass. 37, 24.23 out of 100, or 0.2423, have this mass. So we take the percentage and turn it back into the fraction by dividing by 100, and we multiply by the mass of that isotope. We do that for all the isotopes, and then we add them up, and we get the average mass. We don't have to divide by the number of them, because that gets incorporated into here with the 100 business. Any questions? We'll do an example. Okay, magnesium has 3 naturally occurring isotopes, masses of 23.99, 24.99, and 25.98 atomic mass units, natural abundances of 78.99%, 10%, and 11.01% respectively. Calculate the atomic mass of magnesium. So they're listing 3 masses, and then they're listing 3 percentages, and they say respectively. That means they're paired up in the same order. So the first one in this list goes with the first one in that list. So what we want to do is we want to take the percentage and make it into a fraction, 0.7899, because 78.99% means 78.99 out of 100. If you divide that, this is what you get. So that's where I'm getting that from. We're going to multiply by the mass of that isotope. So that's this guy here, 23. 24.99 atomic mass units. And we could do each of these together and then add them up. I find that tedious, so I'm going to just run them all together and do it at once. 10%, so that's 0.1000, and the mass of that one is 24.99. And then we have 11.01%, 0.1101, times the mass of that one, which is over here, 25.98 atomic mass units. And our calculators will understand if we just go left to right. So 0.7899 times 23.99 plus 0.1 times 24.99 plus 0.1101 times 25.98 equals. So my calculator, as usual, is giving me more digits than I need. It's giving me 24.309099 atomic mass units. How do we do sig figs on that? We're just going to do approximate sig figs on that. So our percentages had 4 significant figures. Our masses had 2 decimal places. So there's multiplying here, and then there's also adding, right? So over here, I'm going to go for 4 sig figs and 2 decimal places. So that's going to be right here, 24.31. It'll usually end up the same as the masses, but sometimes they'll give you a whole bunch of digits on the masses and only 3 digits on the percentage. I'm not going to try to trick you with sig figs on these guys. Any questions? Yes? Mm-hmm.
The other way around, so you're finding the refractions.
Yeah.
For that, should we keep on doing it this way, or can we use the math paper for that, like x plus y?
Yeah, so that's a good question. So in the worksheet, there's a question where you do this and you calculate the average atomic mass, but then there's a couple of questions that are kind of sneaky. And they'll give you some information and say, well, what's the relative abundance? Or what is the missing isotope mass? And so then what you want to do is you want to set this up in the same way, but put in an X for the thing that you don't know. There will also be some things that you can figure out, but they're not actually going to tell you. So what is true of the 3 percentages here? What do they add up to? 100. So if you have 2 isotopes and they tell you one is 75%, what's the other one? 25%, because they have to add up to 100. So they're going to expect you to know how to do that. The other thing is they won't always give you this average mass if they're asking for one of these things. Where could we find the average mass of an element? On the periodic table. We can also use this to check our work, because this is magnesium, and if we look at magnesium, 24.3051, 24.31. Just another tip about averages. If you end up with an average that's higher or lower than the range of numbers, something went badly wrong. Okay, so there's the answer. Anybody curious how they find out the mass of those different isotopes? You can't just pick them out of a group and stick them on the balance. And how do you find the percent abundance, right? So an important instrument for doing that is called a mass spectrometer. And this is a simple illustration of one. We actually have a mass spectrometer attached to our gas chromatograph in the instrument room. So the sample is made into a gas, and you inject it into this end, and then it comes through here. Well, actually, it's not necessarily gas there. The heater vaporizes it if it isn't. So it gets vaporized into a gas, because liquids don't float through the air very well. Becomes a gas, and then it comes over here where we have an electron beam that ionizes the sample. So that's going to turn all of those atoms into ions. We want to do that because then you can use an electric field to accelerate them. So we use an electric field to accelerate the particles, and then we shoot them through a magnetic field, and the magnetic field is going to cause their path to bend. The lightest particles will bend the most, and the heaviest particles will bend the least. So it's like, a bunch of wagons or something coming past you, and you're standing here and you're giving them a shove and trying to push them off course. If you've got a really big heavy wagon and you shove it, it's not going to change its direction very much. But if it's a really light wagon and you give it a shove, it could change at quite a big angle. So that's what the magnetic field does. So then there's a sensor over here that detects when the particles hit. And so we're separating them according to their masses. It works for pretty much anything. You can use it for compounds. You can also use it for elements. It's really cool. So the sort of information you might get out of a mass spec is going to look like this. And it's going to show you the mass, and the intensity, the relative intensity is going to give you the percent abundance. The calculation is a little bit messy, and I'm not going to ask you to do that, so we're just going to skip that. And if you want to talk about it later, I'd be happy to talk to you about it.